Hello, this is co-author and presenter SeungBum from South Korea. We are in Ulsan National Institute of Science and Technology Graduate School of Artificial Intelligence. Now, I'm gonna introduce our paper MetaVers, Meta and Versatile Representations for Personalized Federated Learning. Before we start, we have to know about the differences between traditional learning and federated learning. First, traditional learning, which is also called centralized learning, is that the data is collected by the server to train the model. All clients should send their data to server. But in federated learning, clients train the model directly by receiving models without sending data. The server collects all the local updated models of clients, and the aggregated models is sent back to the clients. It is necessary to look at the difference between these two learning methods from a privacy point of view. In traditional learning, the server's access and ability to view the client's local data during the model training represent a significant privacy leak. But federated learning is a decentralized learning approach where a central server trains the model directly on individual devices, keeping personal data localized to preserve privacy. But because of data heterogeneity across clients, it becomes challenging to converge a single model as it becomes diverse models after local updates. And it is also tricky for the single converged global model to respond specifically to each edge device. So the personalized federated learning aims to addressing data heterogeneity by having clients to have a personalized model. Various studies have been conducted so that global model can be updated in a better direction. There are diverse strategies of previous works such as regularization, model mixture, database methods, or clustering. So we thought that meta-round representation which gains general ability by learning various tasks would be possible to learn stably and respond well to clients different from the overall distribution. Then we have to think about these points. How to get meta-round representation or better representation that is not dense, and how to find the suitable margin value in representation learning, and how to safely train on gradient-based attacks. Focusing on these points, we propose a MetaVers. MetaVers consists of two pages, training page and test page. Let's see the training page first. MetaVers acquires a versatile representation by meta-learning and margin-based learning. At the start of every round, each client constructs his own training episode. MetaVers utilizes two loss functions, Euclidean distance-based cross-entropy loss and triplet loss. MetaVers updates local embedding network with local episodes via episodic training. After construction of local episode, first, calculate the prototypes with superset using embedding network taken from the server. In the figure, the average of the blue scale data points would be prototypes, and compute the cross-entropy loss with the query set and prototypes. And secondly, triplet loss. To avoid dense embedding, triplet loss is employed for the global network learned through local episodes. Each prototype is set as an anchor point for more efficient computation and performance. When a small green circle is an anchor point, the green data point above it becomes a positive point, and the blue data point becomes a negative point. For compute the triplet loss, we need margin value m star. M star is dynamic margin value, obtained by taking the larger value among the average distance between the class centroid and the aggregated local margin value. Local margin value is calculated as the average of distances of anchor points. We can get a global margin by getting the moving average of past global margin values with a fixed interval of W rounds. And using max function with local margin and global margin, a client can get M star value. This means that each client pursues the larger margin space when it does not show sufficient margin space compared to the average. Let's see the overall diagram of MetaVers. Therefore, clients send local updated models and local margin values to the server every round. And the server aggregates the local models and compute the global margin. and the further sends the global model and global margin to selected client. These processes will be repeated. After all the training is done, the server sends a well-trained embedded network to each client. MetaVers computes local prototypes as the local classifiers with a local dataset. Based on the representation of each client's trained dataset, each local classifier predicts the class of closest prototype. Now, let's move on to experimental setup and take a closer look. To compare MetaVers performance with other PFL algorithms, we followed the experimental setting of prior works personalized pattern learning using hypernetworks and with Gaussian processes. This benchmark is more realistic and challenging scenario compared to the other benchmarks. We set the number of clients to 50, 100, and 500, but the number of participants for each round is only 5 for all cases. And we trained global model up to 1000 communication rounds. We use datasets 5x10, 5x100, and Phoenix 10. Data distribution is designed so that each client selects a specific number of shards. And we use the LUNET-based model, but per MetaVers, the left classifier layer is dropped. This is the main result of our experiment. Our method test accuracy was higher than any other method. MetaVers performs significantly better than similar methods per pad average in that it utilizes meta-learning. MetaVers is better than Federated, KNN4, and PadBabu, which find global representation among existing methods. I think it's because MetaVers got better parallel representation. We conducted more experiments to show strength of MetaVers. To see the effectiveness of loss functions in our method, we trained using only one of the two loss functions. MetaVers with dynamic margin shows the best performance over the version of cross-interrupt loss and the fixed margin triplet loss. To analyze the representation of our method, we calculated normalized variance of global representations. Normalized variance value is the mean of per-class variance of features divided by the scale distance to the nearest interpolling prototype. The result shows that MetaVers makes a compact and separated representation across clients compared to other shared representation-based methods. We conducted TFNE visualization to see representation ability. As you can see in local TFNE visualization, prototypes are centered and overlapped. MetaVers is the only case where the centroids are sufficiently well separated without overlapping. It means that MetaVers can make well-clustered and separated representation. To see the generalization on noble classes performance, we calculate the accuracy on a newcomer with 5 unseen noble classes from test split following the setting of pure round learning. MetaVers still perform better than other algorithms. MetaVers can respond well to newcomers with noble classes without additional learning. Now, we have to consider privacy issues. According to the gradient-based attack proposed in previous studies, it is not safe to exchange model in itself. But in our method, the server of MetaVers cannot access the local class prototype, so the loss computation at the local client cannot be rehearsed even with the shared gradient. We can see the qualitative result against dim leakage from gradient in next slide. This result shows that MetaVers can train an effective representation without taking the risk of private data leakage. Fed average, which shares the entire model, is vulnerable to gradient-based attacks while MetaVers is not. If prototypes are leaked, it becomes vulnerable to attack. However, leaking prototypes corresponds to a level of information exposure that is not different from the data exposure. In conclusion, MetaVers can make meta-trained global representation that captures the commonality across heterogeneous clients to solve the personalized pattern learning problem, and able to respond to newcomer clients of unseen data distribution without additional learning through a parallel representation. MetaVers achieves a state-of-the-art performance. Thank you for listening. If you have any question, you can contact us by an email.